for an AC voltage source. So the other symbol that we've been looking at, where we use the dashed lines, a lot of people say it's a symbol for a battery, but that's not exactly true. And what I'm going to miss is my PowerPoint, my drawing on my PowerPoint. So this is real big. So this is the symbol for a DC voltage source, right? Okay. This is the symbol we use to represent an AC voltage source. And I can change, I don't see where I can change the size. I'll just have to live with it. So what happens is, I have to remember how to turn it off. Okay, there we go. So what happens when we generate AC, we generate it on what we call a sine wave. And a sine wave has this basic appearance right here. So a lot of people think AC, when we do AC, it's generated like this. But it's not. It's generated on what we call, it's got a waveform. This is not exactly accurate. What happens is it usually takes off and goes up almost vertical. Then it'll come up here and it hits what we call a peak. And then it'll drop down and go back down to what? 0. Then it'll change directions. Then it'll go to another negative peak. And then it'll come back up like that. And this is the way we generate a sine wave. Now, how it got the name, and originally, and it's still done that way, is we generate this thing on a circle. Originally, we had a north and a south pole. Y'all know what's required to produce magnetically produce an EMF? First, we got to have a magnetic field. It don't want to write. 2, we've got to have a conductor. And 3, we've got to have, we call it motion. They call it relative motion, but it's not just motion. The conductor has to move through the magnetic field. So we have to move it through the field. And if we was over there in the motor control lab, I could show you this. We got a big old voice coil that came off of a voice coil magnet. It came off a real old disk drive, and it's about this big. We got some rolls of wire, and we just swing it off the magnet, and we make those. And this is the way Alabama Power works. This is the way your alternator on your car works. So what we do, we got one of two options. We can move the conductor through the field, or we can make the conductor stationary and move the magnet. And that's the way your alternator works. So if you looked at your alternator, you'd have all these coils of wire around the outside. And what we're doing is we're spinning an electromagnet. Y'all know what an electromagnet is, right? Everybody okay there? I don't know where my electromagnet's at, but it's up there somewhere. So when we swing this thing by a north and a south pole, what it would do is it would create a sine wave. So what was happening is we'd have that magnetic field. And what determines the amount? Well, the number determines the amount is the strength of the field. So this is what your alternator does. Your alternator is spinning what we call an electromagnet. And one of the advantages of electromagnet over a permanent magnet is we can change its strength. So that's what's spinning on the inside of your car. It's an electromagnet. So you'll see some brushes running in there, and then it runs up to some coils. And what happens is they control the strength of the field. If they control the strength of the field, then they can control the what? The output of the alternator. So your regulator, that's what it's doing. If the output tries to drop down, it increases the strength of the field. If your output of your alternator tries to go up, it decreases the strength of the field and lets it maintain a pretty standard output. Another thing we can do is we can change the number of conductors. And what we do is we loop these conductors. And if you think about it, each conductor represents a little old tiny battery hooked in series 80. And we do this by looping the conductor. So when this one passes through the South Pole, the other one's passing through the North Pole, right? You understand that? And then all these little batteries are doing what? They're adding up. And then when we swing this around, this will be going through the north, this will be going through the south, and now they're cutting the lines in a different direction. What will it do? It'll generate the opposite polarity. Well, what were happening when we were spinning that thing around, when that conductor is sitting out here, it's not cutting any lines of force. And then when it starts moving through here, it's moving through an angle. So the analogy we use is walking across railroad tracks. So what you're doing is at first you're going parallel with them, right? And you're not crossing them. And then what you do is you tilt a little bit. You're going to cross them, but it's going to take a little time to cross them. And then what happens is when you go straight across perpendicular, you're cutting them that's when the speed goes up, right? You understand? So if you can visualize this thing swinging out here, when it's out here, it's moving perpendicular and it's not producing any voltage, and would be where? Would be right there. As soon as it starts swinging up, it's going to cut lines, but now it's going to be cutting them at an angle. We come up here and get at the very top, we're cutting them at 90 degrees, so that's when we'll get the maximum voltage. As soon as we do that, we swing over here, and now we're cutting them at an angle, and it takes time to go through the lines, so our rate of cutting goes down. And then it'll move along, and we'll hit out here, and what are we out here? We're back in parallel, I mean perpendicular to them, and we're not doing any voltage, so now we're right here. And then what would it do? It would do the same thing on both sides. And what this did is it generated this waveform. So here, we do 0, we start cutting them, we come up here, we hit a peak, and as soon as we hit a peak, as soon as we hit that peak, it changes directions and starts coming down until we hit 0. So what they came up with, they say, well, if this is generated on a circle, a north-south pole, then we will call this 360, but we won't call it circular degrees, we'll call it angular degrees. So here we're right at 90 degrees, here we're back at 270, here we're at 180, here we're at 270, and here we're back at 0. But what you have to understand, 0 and 360 are exactly the same thing. So 360 is just like midnight. What's midnight? What's 12 midnight? It's the end of one day, but the what? The beginning of another. So that's true. So as soon as I get over here, then I'm back over here again, and I start the whole thing, and this thing is just spinning. So these waveforms occur all just one after the other, and how long are they there? Well, they're as long as Alabama Power is producing power. Up here, they're on this as long as we do what? As long as we don't turn off the power switch, right? Everybody okay? So this right here would be 90 degrees, and this right here would occur at 180. And this guy's doing awful, by the way. This would be what? This would be 270. This would be what? Well, it's going to be 0 and 360. So it's going to be 0, it's going to be 360 of this alternation, but it's going to be what? 0 the next. What would you think half voltage would occur? So let's say this right here is 10 volts. What angle would you think half voltage would occur? If this is 90 degrees. Most people say 45, but it's not this. If it was this right here, it would be 45. But it's not that, it's a sine wave. And how did you get the name sine wave? Well, what we can do is we can take so if I come up here and drop this down, or if I come over here from 0 and drop it down, this creates what we call a right triangle. And what we're trying to do is we're trying to calculate that side right there. We call it the instantaneous voltage. And that will always be the sine of the angle. So you can take VP, always take VP, and you can multiply it down the sine of the angle you want to know the instantaneous voltage, and it will tell you the voltage at that point. Half voltage is 30 degrees. So if you look at the sine of 30 degrees, it's going to be 0.5. If you look at the sine of 45 degrees, it's 0.707. So it's actually up to 70.7% at 45 because it's not a linear waveform, right? You understand? So since the voltage varies with the sine of the angle, of the electrical angle, we call this thing a what? A sine wave. That's how it got its name. And so we can get the instantaneous voltage of any angle. And that 0.707 is going to become pretty important because that's the average value of an alternation. Oh, I don't have that over there. So I'm going to have to turn this off. So this is power, this is a PDF file is what it is. So AC has no polarity. Because why? Because it's constantly switching. Alabama Power generates these as 60 waves per second, or 60 cycles per second. We'll look at that in a minute. So that means a whole cycle takes 18.6 milliseconds. It swaps polarity every 8.3 milliseconds. It changes polarity. It's only at peak for a time that we just can't understand. So it's something that's constantly in motion, right, and moving extremely fast. So it actually changes direction. So we have no negative and we have no positive. So on a DC circuit, if you hook this thing in here backwards, if you got an analog meter, you can mess it up putting it in there backwards. On this one, if you hook it in backwards, these are going to measure, but when you're expecting positive, it's going to measure what? Negative. AC, it makes no difference. On AC, these guys here make no difference. And I've heard people say that. Well, you got to put your back lead on the neutral. Jeez. So AC, you can do that. This way it'll measure 120, that way it'll measure 120, and it won't have a sign up there because it has no sign. So these things move in waves like this, one after the other. One repetition is just like we call cycles. So cycles are things that repeat, right? We move in cycles. So that's what we call one repetition of the waveform. We refer to it as a what? Cycle. So this would be a cycle. This would be a cycle. This would be well, that's not true. A cycle is the same point to the same point. So literally we could say this right here would be a cycle also, right? You understand? So when you measure the time for the cycle, you can measure it, as long as you measure it on the same waveform to the same waveform, that would be the what we call the period. This is a cycle. But when we start measuring the time, you literally can measure the time anywhere, right? So what do we call this? Yeah, we call it a cycle. I need to find the PowerPoints on this. Now the rate of the cycles, we call that the frequency. Everybody okay? That's got to be real slow. I'm just going to stop right there. So what is this? This is the rate of the cycles, measured in cycles per second. And like we talked about another class, people who are real fundamental in the development of a science usually get the honor of getting their name placed to something. So we got Hertz, H-E-R-T-Z, which is the guy that was fundamental in the development of the. So Hertz stands for cycles per second. So the way you abbreviate it, you'd put like 60, you'd put an uppercase H and a lowercase z. That's why you abbreviate Hertz. So Alabama Power generates 60 Hertz, which is 60 cycles every second. Everybody okay? we have different, we call this an alternation. So every cycle consists of a positive and a negative alternation, which makes sense, right? Come on. So this would be the positive alternation, this would be the negative alternation. Every alternation has something that we call peak, so we call this VP, and this VP would be exactly the same as that one. In fact, if we was to take this and flip it around and put them on top of each other, you can tell them apart. They are mirror images of each other. It's just that one of them's negative and one of them's positive. Everybody understand that? So when we talk, we'll be talking about V peak, and we'll be talking about V peak to peak. And so we'll abbreviate VP. This is what we're going to use for V peak, for V peak to peak. Well, let's call that VPP. We okay? That makes sense? So if you measure V peak, how would you calculate V peak to peak? Multiply by what? By 2. Everybody okay? So we're going to be using a piece of test equipment that we call an oscilloscope. If it pops up. And we're going to be using digital oscilloscopes, and we'll talk a little bit about that. So let me fire this thing up. This is called a function generator. What we can do with function generators is, and it's not working. So don't tell love technology. What we do with a function generator is we use it to generate AC waveforms. And what's nice about the function generator is that we bring AC in, we convert it to DC. And what advantage does DC have over AC? We can electronically control it. So we can use that DC to convert it back into AC. But what's nice about the AC is we can control the amplitude now, and we can control the frequency. The only way you can control the amplitude of Alabama Power is to send it to a transformer. And you can either step it up a certain ratio or step it down a certain ratio. Okay. You can't change the frequency. So this is the different AC waveforms that we can generate. Of course, this guy right here, if y'all can see it, this would generate a sine wave. This would generate an AC pulse waveform. And this should generate an AC triangle, what we call a triangle wave. Of course, we got it set up to do what? And then when we look at the scope, what the scope does that a meter doesn't do, a meter averages everything. So what you're looking at is a basic average, right? Understand? Well, we'll talk about that in a minute. An oscilloscope shows you exactly what's there. And it shows you what's there relative to time. So the horizontal control right here, it says horizontal, this is rated in time per division. And then this is your vertical controls, this is volts. So this is time this way, and this is volts that way. We'll talk about this later. So what we're doing is we're looking at an AC sine wave. And if you can see this little red line, this little thing right here, this represents 0 volts. So it goes up here, hits peak, come down, and you can see it starts up real fast, starts leveling off, hits peak, and then does what? Drops down, hits this again. What's this? This is 0, right? And then it goes down and hit peak, come back up, hit 0, and then it just does what? Repeats over and over and over and over again. So what we can do down here, it says that I've got it set on 2 volts per division. So we have 2, so here we're talking about major divisions. Can y'all see the major divisions here? So 2 volts per division, this would be 2, 4, 6, 8, 10, 12. That would be what? 12 volts peak to peak. Or 6 volts peak. But your scope measures peak to peak. It shows us exactly what's there. Now the time, which we have set here, I have it set on 10 microseconds per division. So what I'm going to do is, what we want to do is get this on a starting point. So we have the ability to move that. Okay. So now I'm measuring 10, 20, 30, 40, 50 microseconds for that cycle. Are we okay? Or close to it? And we'll talk about minor divisions later on. So this is showing us exactly what's there. Now what is our meter going to measure? Well, that's what we got to figure out. So let's see what's on the next slide. So the time per cycle, so what I just did is I measured what we call the period. So the period is what? So we have the cycle, right? It's not right. Then we have the what? Frequency. This is off Blackboard, by the way. And then we have the what? Huh? No, I'm not. I don't cuss. About my word is crap, so they can say crap at home. Of course, my preacher says that, so I'm okay. So frequency, and then the time for the period, we call it what? I mean, the time per period, we call that the period. The time for a cycle, we call that a period. Y'all go ahead and take a break and figure out what's going on. Well, it's not the lagging. It's lagging of something to do with this. Of course, it might be. I'm uploading. All right, I found my PowerPoint, so we should be okay now. Well, it should be. So what do we got? We got frequency. And what's this? Yeah, this is the rate of the cycles. We got cycle. What's cycle? Well, we say it's one repetition of a repetitive waveform, right? Well, that's what a cycle is. One repetition of a repetitive waveform. What's frequency? The rate of the cycles, in cycles per second. So it's either going to be given in CPS or what? Hertz. Then we have the period. The period is what? Yeah, the time for a cycle. So up here, we measured our period on the oscilloscope, and we measured 50 microseconds. Now, period and frequency are inversely proportional. Do you know what that means? Now, when numbers are inversely proportional, how do we find the other? Does anybody know? Well, yeah. We take what we call the reciprocal of it. So this is why we do this a lot. So reciprocal will give you the inverse equivalent, right? You understand? So we can say the frequency is equal to 1 over the period. We usually label the period T. We usually use an italics T, so we don't get that confused. So it means in our situation, we should say, and by the way, raising the number to the -1 is also taking the reciprocal of it. So some calculators, the reciprocal P is labeled x to the -1. Some of them's got it drawn as a reciprocal. We use this a lot because what's it going to do? It's going to give us the inverse of something that's inversely proportional. So this would be 1 over 50 microseconds. We don't put the micro down there. And what would we come up again? Yeah, 20 kilohertz. Well, if I know the frequency, so let's say I got 15 kilohertz and I want to find the period. Well, the period is the inverse of the frequency. So period is equal to 1 over F, and F is equal to 1 over period. Now, the problem is this oscilloscope is it's a digital oscilloscope. It's a computer. So we can make this oscilloscope display the frequency. We can make it display the period. Right now, we got it set up to measure the period. Okay. A standard analog scope, which are still very popular because of the price. This oscilloscope we have here is about $500. You can get a nice analog scope that'll do this same measurement for around $250 for half the price. So analog scopes are still very, very popular because they're very cheap. Those things don't measure frequency. They measure time. So if you measure the time, then you can do 1 over the time. That will give you the watt, the frequency. So if I want to measure a certain frequency on my scope, then I would take the frequency, I'd take the reciprocal of that, and that would tell me what it would measure, the time it would measure on my scope, right? Does that make sense? Or if I measure a time on my scope and I want to get the frequency, I take the reciprocal. Does that make sense? And of course, what's nice about a function generator is a function generator, if it's not going to display on me, a function generator, this is a cheap function generator doesn't have this, but we got 2 pieces of test equipment in this one. We got one we call a frequency counter. And it's a digital device that measures what? Frequency. We got another piece of test equipment we call a function generator, which we use to generate waveforms with. This guy has a built-in function generator on it, which is really nice because this is showing me that I'm measuring 20 kilohertz, right? And of course, we did that on our scope. So what we did is we verified to make sure it was okay. The more stuff you get on the function generator, if you're into troubleshooting audio equipment and stuff like that, then these guys are invaluable. Because have y'all ever seen audio before? I mean, it's all over the place. And you can't figure gains. You can find signals, but you don't know if it's working right. Well, this guy right here, you can inject a set frequency into it, and you know what you're putting in, and you know what you can measure what you're getting out, and you can actually get the true gain. And we'll talk about gains later on when we get into that. So everybody okay on those things? 60 cycle, the period would be 18. The period would be 16.67 16.7777 milliseconds. So if you got your calculator, if you took the reciprocal of 60, right, it would come up and give you 16.77 milliseconds. So one alternation is going to be 8.8. It's going to be 8.3353 milliseconds, and we usually just stop at 8.3. Are we okay? Any questions on those terms? Everybody okay on peak and peak to peak? That's going to become very important on how, when we come in and try to calculate how much DC we're going to get out of this thing. Peak to peak, everybody okay? Now, what they did is they said, okay, we need to figure out what work we're going to get out of this thing. And they were looking for what equivalent DC they would get out of this. So if I had so much voltage AC, 120 volts AC, I want 120 volts DC worth of work, right? You understand that? But the problem with AC is that it's constantly changing and it drops down to 0. So they said, well, let's average this together. So they started out doing what? Doing an average. And what's the problem with doing an average? I'm in the wrong thing. I need to be in my PowerPoint. Well, the problem with doing an average is that the average of a cycle is going to be 0. And why is that? Because for every positive you have, there's a negative that cancels it out. So if I do an average, it's going to appear that I get no work out of this. Y'all understand? So if I was to come up here and go, what, 1? So if I was to come over here and have 1 volt there, well, let's do one of them, so just to get a feel. So I'd say 1 volt here, that'll be a +1. And I take 1 volt there, that's a -1. I add them together, I come up and get 0. I divide that by 2, I still get 0, right? So they said, well, we need to come up with another method where we can figure out this voltage. We don't call it an average, we call it an effective voltage, because it gives us the same effect as that. What they do is we use what we call the root of the means of the squares. Of course, we drop that down a lot and call it RMS. So what we do is we come up here and we take a +1, which we'll just say 1. Let's first of all, I'm going to go back. I'm going to take the square root of a -1. What's the square root of a -1? I mean, what's a -1 squared? Excuse me. Yeah, so if I take -1 and then I square it, it comes up and makes that positive. And then I come up here and I add that to a 1. Now it comes up and gives me 2. And when I divide by 2, it gives me an average of 1. Right? You understand that? So what that means, if I took an infinite number of voltages on the positive alternation, I took the same spacing as that on the negative alternation, and I squared everybody, right? You understand? Then it would take the negatives and turn them into positives. But a -2 would square to a +4. Everybody understand that? So that would be doing what? That would be doing the squares. Then I take the mean. What's the mean? The mean is the average. That's another term we use for average. So we square everything. So every positive, we use a negative that offsets that, right? You understand? So if I use a -1 over here, I'd use a -1. And we'd use a lot of them to get a feel of actually what it would be. Then when we get through, we take the square root of the answer. The root of the means of the squares, and we refer to this as RMS. And this will give us the effective voltage of 120 volts. It's an average, but it's not an average, right? You understand what it's doing? Everybody okay? That makes sense. So that's what we measure. So if I come up here and I say 120 volts AC, we take for granted it's actually what? RMS. So that means if I've got a 120 volt AC source and I run it into a resistor, and I take 120 volts DC and I run it into that same resistor, I get exactly the same amount of work. Exactly the same amount of work. Now, if it is a sine wave, If it is a sine wave, you can do this all day long, and it would always, VRMS would always come up to be equal to VP. We usually use the positive peak, so we don't come up and get negative, times 0.707, which is the sine of 45 degrees, which is exactly in the center of the waveform. It would always come up to be that. You can work it all day long. So if I know V peak, if I measure V peak on my scope, I multiply it by 0.707 and it's a sine wave, it will always give me the effective value. Of course, we rounded at 0.707. If you took the sine of 45, it's going to be 0.707070707. Now, if it's a non-sinusoidal AC waveform, this don't work. It only works on a what? On a sine wave. So when I look at this meter, it says nothing. And we didn't have these other meters until we got microprocessors, by the way. It says nothing. So this meter right here uses 0.707 when I put it on AC. So if I measure a non-sinusoidal waveform, AC waveform on this, it's going to measure something, but it's not going to measure it right. If I spend a lot of money and I buy what's called a true RMS meter, this has a microprocessor inside of it. So this is down here at the bottom, it's labeled. Can y'all see what that says? True RMS. This meter would measure, this would give me the DC equivalent of no matter what type of AC waveform I measure. So which one are you going to buy? I'd probably buy this one. Because I know if you're in residential wiring, commercial wiring, you know, if you buy a true RMS meter, you're wasting your money. If you're into variable frequency drives or variable speed AC drives, those things generate, they generate non-symmetrical waveforms, or switching power supplies generate non-symmetrical AC waveforms, then you need a what? You need a true RMS meter. So it depends on your application. But you're talking the difference between quite a bit of money for the same features between the two meters. So if you're an electrician and you buy a true RMS clap-on meter, you just, for about $300, you what? Wasted a ton of money. You can buy a real good meter from a real good RMS meter from Craftsman, pay $50 for it, do everything you want to do in this class. So that thing actually calculates RMS. And it's called a what? True RMS meter. Are we okay? Everybody okay? Now, the average if we did this in what we call radians, y'all know what a radian is? I know what a radian is. Do you know what a radian is? So if we took a circle, so this is generated on a circle, right? And if we took a radius of the circle, like this, if we took that radius and laid it out across the outside, it would be about 57 or something degrees. That is a radian. So a radian is actually a length. Does that make sense? Everybody okay? If you take a radian and you multiply it by 2 pi, you will come up and get the lengths of the circumference of the circle. So 2 pi times the radian, 2 pi rad, this is the circumference of the circle. So they come up here and divide this thing up in radians. We don't have enough time, but this is this right here. So on a waveform, this is going to be considered to be the radius right there, because that's when it's at the maximum, right? You understand? So if I was going to come over here and put a 0 and start swinging this thing around, and then I drop a horizontal to find that, well, right here, that's when it would heat peak, and that's when this right here is going to be equal to the radius. So you're going to find in AC, when we start dealing with actual values, not displacement, values, we're going to use this 2 pi rad formula all over the place. Does that make sense? So when we calculate the average DC voltage for this alternation, we're going to use 2 pi. Make sense? So what would we use? Okay, so we would come up here and say, okay, the DC average of an alternation. Now this is not the DC average of a cycle. What's the DC average of a cycle? 0. So I'm going to find my, it's out here somewhere, right here. 2V peak over pi or 0.637, which whenever you want to use, that's fine. I'll use 2V peak over pi. Because when we start dealing with half wave and full wave, it really makes sense. So if I come over here and strip this one off, so it's gone. What would be the DC average? V peak over pi. Because this is going to be this one plus 0, right? You understand? So the average, the DC average of this, the DC average is going to be equal to V peak over pi. If I come over and do this, then it's going to be 2V peak over pi. So that's the way we calculate the DC average. And we'll look at that in a minute. And you can say that what's the DC average of a cycle, and it'll be on the test. It'll say 2V peak over pi, and somebody in this class is going to answer that. The DC average of a cycle, did I say it right, is what? 0. The DC average of an alternation is 2V peak over, or 63 V peak times 0.637. But when you look at the textbook, it's going to say 0.637, but I wanted to show y'all where that came from. That's the guy I like to use. So everybody understand RMS now. So RMS would give us the same heating effect into a resistor. But when you get into AC, you're going to learn some weird stuff in AC that we don't have to deal with right here. And so AC creates something called reactance that does absolutely no electrical work. But we don't have to deal with that in this class. So 0.637, y'all know where that came from? That's the average of a wall. Alternation, but I like to use 2V peak over pi. You know, sometimes little things stick with you. Like one of my instructors taught, when he taught the area of a circle, that's what he said. 2 pi rad. It was 2 pi squared. And he said, or pi squared. Pi, he said, pi are not squared. Pi are round, so I remember it ever since. I don't know why we got that in there. Everybody okay on degrees? Talked about that. Everybody okay on degrees? In this one, it don't make much. In this class, it doesn't make a lot of difference. Later on, when you get into AC, you're going to get into what we call phase shifts, where you actually shift the current and the voltage in a circuit, and you're going to be leading or lagging by a certain amount of degrees. And to correct for it, you're going to have to know that, but we don't need to know that in this class. There's a radian. Y'all understand a radian now? So a radian is when we do what? We take the radius of a circle and lay it on the circumference. So the radian is actually a physical measurement. This 57.3 degrees is a displacement. These are rads in circles. So if we did radians, so a full circle is 2 pi rad, and you can split it down. It don't make any difference. All I wanted to do is show you this 2 pi rad so you'll understand where a lot of our AC formulas come from. So if the capacitance in a circuit is 1 over 2 pi, right? The reductance in the circuit is 2 pi frequency, so that's where all those formulas come from. Because what we're not dealing with a degrees, we're actually dealing with a physical measurement around the outside of the circumference of the circle. So when you get into AC, that 2 pi rad, you're going to run into that all over the place. The only place we're going to run it over here is for what? the average of a DC, an AC alternation. We talked about that. So that means one cycle we could say equals to what? 360 degrees, or we can say it equals 2 pi times. Everybody okay on positive peaks? We talked about sine wave, right? And that's what this is trying to show you, how we came up with the sine wave. So this is how I got the name. Why? Because if we calculate the instantaneous voltage relative to 0, it's going to create a rectangle. I mean, it's going to actually, it's easier to see when you do it like that. And of course, what we would do is we would go up here. So this is actually the sine wave right here. That equals what? V peak plus. This is V peak minus. And what we would do is this would 0, and I would take it up, and then I would drop it down. And then this vertical right there would be the what? Would be the actual instantaneous voltage. And if we took V peak and multiplied it times the sine, that would come up and give us that amplitude right there, right? So in this circuit right here, what's 110 volts? If it's not given, we know it's what? We know it's RMS. Well, how do we go from RMS to VP? If I measured this on my oscilloscope, what would we do? Yeah, 0.707 is the number. Okay. So VP, if VRMS is equal to what? VP times what? 0.707. Everybody okay? Then if I transpose this or put it inside my little thing that you learned in DC, VRMS would be equal to VP times 0.707. Y'all remember how to do that? So what would VP equal to? VP would be equal to VRMS over 0.707. So over here I would say VP would be equal to 110 divided by 0.707. Now, I know it in my head because I know when I say VP, so which is the highest part of a mountain? Peak. So you know VP will always be greater than RMS. RMS is, it's an effective voltage, right? But it's basically an average. Everybody understand that? So if I divide by a fraction, I come up and get a bigger number. If I multiply by a fraction, I get a smaller number, right? You understand? So if I'm solving for V peak and the number is 0.707, so I got to figure out if I want to divide by it or multiply by it. So here I'm going to V peak, so I'm going to divide by 0.707, and what do we get? Yeah, 155.6 volts. Well, my scope does not measure peak; it measures peak to peak. So how would I go to peak to peak? It's going to be equal to V peak times 2. Or you could say, some people say go from V. If we took the reciprocal of 0.707, it comes up to be 1.414. So instead of dividing by 0.7, we could multiply by 2.82. And some books teach all them numbers, right? You understand? And they would give you the right answer. But now you got well, when do I multiply by 2.82? When do I use 1.414? If you just remember 0.707, right? You understand? 0.707. The sine of 45 degrees. And then you say, okay, that'll take me between V peak and understand our RMS or RMS to V peak. And what's the difference between V peak and V peak to peak? It's just what? Times 2. Does that make sense? So how much would V peak, what would my scope measure to measure this? Huh? It's going to measure I can see 310 volts right now. 310. So that's going to be approximate in my head. It's going to measure almost a little over 310 volts peak to peak. And you say, well, good gracious, that seems like a waste. But AC, we can do something with AC that we cannot do with DC. And what's that? We can step it up and step it down. And so we step it up for transmission, and they don't care what the peak-to-peak voltage is, right? You understand, but you got to understand when you look at an oscilloscope an oscilloscope shows you what is there. Your meter is going to average everything, right? Don't understand that. So your meter does not show you what's there. So that means if we got garbage on a DC bus, a meter's not going to show you that garbage. It's not going to show you oscillation. It's not going to show you anything like that. It's going to show you what? Basically an average. Of course, if you got it on AC, it's going to show you RMS, right? You understand that? So an oscilloscope shows you exactly what's there. But it's going to show you peak to peak and not RMS, right? You understand that? Of course, you can tell this guy here to tell you the RMS value on that. So 120 volts at your house, that's about 370 volts peak to peak. But it's no big deal, right? Y'all understand that? That's no big deal. But what we get the ability to do is we can run that AC through transformers and do what? We can step it up to transmit it, and then we can step it down for what? Step it down for safety, step it up for transmission. Because the magic formula is what? I is equal to P over V. What's P? Power. So the higher I can make that voltage, the less current's required to transmit. Smaller gauge wire or aluminum. We can use aluminum wire instead of copper now. Even though aluminum itself is not a great conductor, it's a good conductor. But what advantage does aluminum have over copper? Yeah, cheap. All the way around. You know, not only is it a lot cheaper, it's a lot lighter. So it means all these big old towers that supporting all those wires don't have to be as rigid or as tough as if it was copper. Step it up for transmission, so the current goes way down. Now we can go to copper instead of aluminum. Get it way, way up there, depending on how far you're going to transmit it. They have different voltages they use depending on how far they're going to send it. They got different names. One of them's interstate, intrastate, inter this, and they know what voltage they're going to use for that. Up to almost 800,000 volts to go from state to state. 800,000 volts means I could send 800,000 watts of power with 1 amp. 1.6 gigawatts worth of power with 2 amps. And if it's 3-phase, you get the advantage of the square root of 3, by the way. So it's the square root of 3. So you actually, it takes less current to transmit 3-phase because it's spread across 3 lines instead of just 2. But if I did this calculation, I would calculate, if I was going to do this with my meter, you'd do it just like you did it in DC. Exactly the same way. So we're not going to work any of those. By the way, this is another thing we've got to learn in this semester, is we can take AC and superimpose it on top of DC. And I'll show you all this on the oscilloscope. So our oscilloscope gives us the ability to do something called a DC offset. So right now I have AC. And what I'm going to do is I'm going to put more volts per division and make it. By the way, notice what happens when I change the frequency. So here the frequency is going down. So you can literally see the period spread out, right? So the period's getting longer. This is the frequency going up. So you can see the wave, they're still cycles, they still look alike. So when the waveforms get closer together, that means the frequency's going up. If they spread out, it means the frequency's going down. So that right there is still AC, right? Y'all see that? Still too high. Let me turn this way down. And I'll turn my scope up here. By the way, the scope is taking pictures. And what we have to do is we have to synchronize the scope with the waveform itself. You understand what I'm saying? So, and I could draw this on a piece of paper, but if I didn't give my scope a reference, so if I came up here and drew a wave, this is not going to be, but if I came up here and drew an AC waveform like this, and I don't give it a reference, and it's sitting there displaying pictures, so if I do this and I don't give it a reference, then what does it appear like it's doing? It appears like it's snakish. But if I can come over here and give my scope a voltage reference and only start the display from a certain point, so that might be here and that might be here. But what if I come over here and move from here to here, and even though these cycles occur, if I come over here and go right there next and display that, what does it do? It appears like they're stationary. So what we have to do on an oscilloscope is we have to synchronize the scope with the signal itself. And what we do is we call that a trigger. So over here on the right hand side, we have what we call the trigger. And what I like about this scope is it shows you the actual trigger. See the little white line popping there? And all I'm going to do is I'm going to reference my scope to a spot on the waveform. Now the scope is synchronized with the waveform itself. And what did it do? It freezes. And your TV has to do this too. In the old days, we had a horizontal sync, and we still have that. So the TV station is sending synchronization with your TV. We call them horizontal and vertical syncs. So your TV is synchronized with those pictures because they're sending those pictures at so many pictures per second. And if your TV is not synchronized with those pictures, then it's going to roll or lay over on its side or do some strange things. So your the TV station does exactly the same thing. They send out these sync pulses. We call them vertical sync and horizontal sync. And what does that do with your TV? Well, it causes your TV to synchronize with the pictures so the pictures don't flop around and roll around and wiggle around what this does. So we're doing basically the same thing. Now what's nice about TV, it's at the same rate. But what I'm doing is I'm adding a DC offset. Oops. So that's not AC anymore because we're zero at it. Here's zero right here. So we can superimpose AC on DC. And if I measure this with my DC meter, my DC is going to average. So my DC meter considers this right here to be zero. So it would give you that DC average right down that center right there because the average value of a sine wave is zero. So where would zero be at? It would be right down the center. So if I measure this with my DC voltmeter, it would measure what I have it on 1 volt per division. It measures about 2 volts. And that we're going to have to see that too. We're going to have to understand that later on too when we get into, because it takes DC to cause solid state devices to work, right? You understand that? So when we get into transistors, we're going to have to bias them, and the signals are going to be riding on DC like that. And we'll show you how we strip the DC off and keep the AC too. So we can call this DC changing at AC rate. It has, but the best thing is to say, okay, it's AC superimposed on what? DC. It's not true AC. It's not true AC because it's never what? Yeah, it never changes polarity. So anybody that says DC, the difference between DC and AC is DC is constant and AC is not, and that's false, right? You understand? DC can change, it just never changes direction. So here the DC is changing, but it's never what? Changing direction. So that'll be on the test too, by the way. DC is the same. We get people in DC, you say DC is the same in a series circuit, and they'll think it's the same no matter what resistors you put in there. So they'll say, okay, you calculate 1 amp, and then you change this resistor out there, and they'll say, well, it's still 1 amp because DC is constant, the same in a series circuit. And I keep telling them it's only the same if you don't do what? If you don't change anything. So if you change the voltage, the current's going to change. If you change the resistor, then what? So y'all probably hear that When y'all take DC, you'll probably hear one of your students say that. What happens if I change the voltage? Well, it's going to stay the same because the DC is the same in the series 3. I think that's about it, guys, and we'll be ready to actually start into our DC power supplies. So we can do all kind of neat stuff. This also talks about it. We're not going to deal with this in this semester, but when you get into AC, you not only got to look at sine waves, you got to look at other AC waveforms. And we have 3 basic waveforms. We have what we call a sine wave. Everybody okay with that? And then we have what we call a pulse waveform. Some people call it a square wave, but that's not true. And then we have what we call a triangle waveform. And I'll show y'all these on the scope. So let me take off my DC. Let me take off my DC offset, bring it back down to 0. And I'll change the volts per division on my scope to make it bigger. Your ultimate goal, by the way, is to put enough volts per division so you can get it as big as you possibly can get it without it going off the screen. That's when your scope is the most accurate. So that is a, what type of waveform? That's a sine wave. This is a pulse waveform. My scope is not set up right, so that's why it's doing that. This is a triangle waveform. Yeah, it looks crummy too. By the way, your meter would measure that just perfect. If you had an RMS meter, it wouldn't measure that right. Can y'all see what it's doing? So this is not a sine wave. So that's a sine wave. That's not a sine wave. Y'all see the difference? So so here we notice that it's not varying with the sine of the angle anymore. Because if it's varying with the sine of the angle, it would be real smooth, right? So this guy here can generate non-sinusoidal, but if you had a true RMS meter, then it would do what? Yeah, it would measure that correctly. So that's not a sine wave. That's about a sine wave. That's not a sine wave. A true RMS meter would measure this, but a regular RMS meter would not. So that's the big difference right there, is that it wouldn't give us the actual DC equivalent. Okay, so any questions on basic AC? So everybody okay on what a period is, what frequency is, what a cycle is? Everybody okay on peak to peak, V peak, VRMS? Everybody okay there? Okay, everybody okay on the average of a DC of an alternation? Everybody okay? Now, what will a diode do? Well, a diode will only let current flow when it's forward bias. If we reverse bias, what is it going to do? It's going to block it. So think about what's going to happen if we put AC on that diode. What's it going to do if we use one diode? It's going to block, it's going to pass one alternation, and it's going to do what? Block the next. Okay, I'll take a 10-minute break, and then we'll come back and let me switch over. And we'll start into power supplies. But diodes, we'll look at that. We have a diode lab. I need one more thing. Y'all go. There's one more thing I need to show y'all. Well, go ahead on diodes before we move on. Everybody get up, move around. And they didn't show that on this slide. I got to work on these slides. These things are a problem.